welcome to Topcast, episode 6 about the problem of induction, the first podcast in a series on the nature of science. Professor Russell owned a chicken. Each morning, he would get up early and feed his chicken. The chicken, being an anthropomorphic chicken, thought what a wonderful thing this was and was excited each morning to see Professor Russell come into the coop with the feed. The chicken went to sleep each night expecting that tomorrow the food would come. And indeed, the chicken seemed to be right. The chicken predicted that each day he would be fed. He was sorely surprised then when, on Christmas Eve of all mornings, kind Professor Russell came in to decapitate him. What does the story of Russell's chicken suggest? It suggests this: no amount of observing a certain thing over and again is enough to entitle you to predict that that thing will continue on again, even one more time, let alone 10 more times, or forever. No number of sunrises suggests that tomorrow the sun will rise. No number of breaths that you take suggests that the next won't be your last. In other words, making predictions from the particular to the general is simply not possible. Well, so what? For so many years, it was unclear exactly how science was justified in making the claims that it did. A group of philosophers and scientists in the 1950s worked on this particular problem, among many others. The main group of scientists and philosophers worked in Vienna and came to be known as the Vienna Circle. The Vienna Circle developed a style of philosophy called logical positivism. It was all about the idea that all knowledge comes to us through our experiences, and a purely logical process is the best way to solve a philosophical problem, insofar as there are philosophical problems. One consequence, as they saw it, of logical positivism was the ability to justify scientific theories. Everyone knew by then that mathematics was a deductive system, and they believed mathematics proved its truths with certainty. In the last few episodes, I've argued that this position turns out not to be correct. You do not get certainty in mathematics. As for science, well, if it's not purely deductive, then what is it? How could you justify your theory if it was not able to be purely deduced from the evidence in the same way that mathematics proves its conclusions? The logical positivists came up with the idea of verification. You verified your theory. How? Well, through observations, repeated observations. So if you were Newton, presumably you watched an apple fall from a tree, and then another, and then another, and then another. According to the logical positivists, you then came up with a theory about gravity, and your theory is verified through further observations. Now, you cannot prove your theory. It's not deductive, but well, it's still pretty well justified, isn't it? So the process of verifying a theory, using a method of justification based upon repeated observation, became known as induction. Scientific induction. So scientific induction is supposed to be a process of justification. You repeatedly observe a certain phenomena, like a falling apple, and then come up with a theory, which is then verified by further observations. You are then entitled, based on your theory, to make predictions like, each time an apple falls from a tree, it'll hit the ground. Now, there's a real problem with this. We saw that with Russell's chicken. Russell's chicken observed that each morning the farmer would feed him. He predicted this would continue. He turned out to be wrong when he lost his head and was put on the table that night for Christmas dinner. What's happened here? It seems like induction can go badly wrong. But if induction can go badly wrong, doesn't that surely spell trouble for scientific theories which are justified by induction? Does this bring all of science into question as unreliable and poorly justified? No. No, it does not, because science does not justify its theories using induction. Induction plays no part in the formation of scientific theories, and it never has. In fact, no one ever justifies anything, scientific theories or not, using induction. Okay, that's a big claim. It's a big claim to say that we never use induction. Never? No. It was the great Scottish philosopher David Hume who, around 1740, clearly stated that induction cannot be logically justified, and that this seemed to be a problem for science. But it's not, because science does not rely on induction, and never has. But Hume was one of the first to most clearly express the problem of how to explain just why it is we are justified in believing our scientific theories and believing that they're reliable. He was a smart man who wondered about the nature of cause and effect and how science worked. Hume was right in believing that we cannot be certain of our scientific theories, and he also knew that induction was flawed. So his problem was to wonder, how then are we justified in believing our scientific theories? He wasn't the first. The Greek philosopher Sextus Empiricus, in around 200 AD, mentioned the problem of induction in his writings, and we're going to find that so many discussions in analytical philosophy can trace their roots to one or more of the ancient Greeks. Since Hume, people have still wondered how it is that we can justify our scientific theories. People who still wonder about that today do not realise that the question has indeed been answered. Now sure, this philosophical question had to wait around 2 more centuries for a solution, but the solution was found. It turned out that science simply does not proceed by induction. Science does not work that way. So how does science work then? Well, I'm glad you asked. Forget induction. Well, don't forget it. It's useful to know the misconceptions that many, especially sociologists of science, and those who write some science textbooks, have about science. Induction is certainly a big concept, and it's still debated today. But most of us interested in the philosophy of science, and scientists themselves, know that induction is dead. The problem with induction is that it is simply not a way of justifying things. Induction not only cannot justify scientific theories, it cannot justify anything. It's not a method of justification. You simply are not entitled to reason from the particular to the general. Russell's chicken shows you that. Given a set of observations, the farmer fed me today, the farmer fed me yesterday, the farmer fed me the day before that, and so on. The prediction, the farmer will feed me tomorrow, does not follow. Not only does it not follow, but something even worse than that. A general prediction like this is simply not a theory. A theory explains something. In this case, the thing that requires explaining is the farmer's behaviour. Now, given one theory about the farmer's behaviour, namely that the chicken is a loved pet, then the chicken might very well derive a certain prediction from this theory. One prediction that he might derive would be, well, the farmer will continue to feed me. And he believes that this is justified because he believes in the theory that the farmer loves him because he's a pet. But given another theory to begin with, another, as it turns out, more accurate theory, namely that the chicken is being fattened up for Christmas dinner, then another quite different prediction would be derived. One day this feeding will stop when the farmer wants to cook me. So given nothing but a set of observations, namely the feeding of the chicken repeatedly, we are not entitled to predict anything just yet. We first need a theory. Next, I'll explain how that works in science. So how do we reason in science? The scientific method is not about verification. It's about falsification. We'll get to precisely what that means in a moment. For now, let's also look at how the inductivists get science wrong. The idea that induction works at all forms a significant part of how some TOC texts and the TOC guide explain how science works. The inductivist idea suggests that scientists make observations, and on the basis of those observations, generalize a theory. We have seen this does not work, and it cannot work. So what do scientists do then? Well, what scientists actually do is solve a problem. They're problem solvers. Currently, for example, the world's cosmologists have a problem. The rate of the expansion of the universe is greater than expected according to general relativity, given the amount of mass and energy in the universe. The rate of expansion is accelerating. That's a problem. One proposed solution is what is called dark energy. This solution itself raises questions because when the mathematics of quantum theory is applied to dark energy, we get a value for the equivalent zero-point energy, as it's called, to be 10 to the power of 120 times greater than expected. This is another problem observed. In fact, it has been said that this is the worst theoretical prediction in the history of physics. We need a new solution. So this is how science works. Problems require solving, and phenomena require explanations. Here's a historical problem from science. Why is it that all the objects in the sky seem to rise in the east and set in the west? The sun, the moon, the stars, and the planets. One solution is that the Earth is a motionless sphere in the centre of the universe, surrounded by a bigger sphere called the celestial sphere, which itself rotates. Now, holes in the celestial sphere give us the appearance of stars in the sky. But now there's a problem. This particular theory can't account for the fact that the planets appear not to be fixed to the celestial sphere like the stars are. They appear to wander about the sky in rather random ways. That's a problem. Now, one solution was to give up the idea of the celestial sphere, but keep the Earth at the centre. In general, theories with the Earth at the centre are called geocentric theories. And you can have a geocentric theory in which all the planets are objects that are in orbit around the Earth. However, these planets don't go around the Earth in simple circles, but rather in complex orbits called epicycles. The notes to accompany this talkcast have a diagram explaining what epicycles are. The purpose of the geocentric theory and epicycles was to explain the problem of why it is that the planets appear to wander across the sky. The astronomer, Ptolemy, in 300 BC, developed this theory to such sophistication that it was able to predict the motion of planets to a high degree of accuracy. This theory was terribly complicated though, and as time went on, it was obvious that Ptolemy's predictions were not as accurate as they first seemed to be. The theory required ad hoc revision. The theory was kept, but it required the revision of putting epicycles onto epicycles onto epicycles. Every time a planet deviated from where it was predicted to be, astronomers just added another epicycle. Clearly, this was unsatisfactory. It was Copernicus who suggested that really things would be much simpler with the sun at the centre and the Earth and other planets going around it. That requires fewer assumptions, and you do not need all these complications of epicycles. Later, Galileo and Kepler would further improve the theory with precise mathematics and the idea that the orbits were ellipses, not perfect circles. Now, perhaps you've heard of Occam's razor. I'll have more to say about that in the next episode on science, but let's just say for now that even in the absence of better predictions, the heliocentric theory, the theory that the sun is at the centre, beats Ptolemy's geocentric theory, not necessarily because it makes better predictions, indeed at the time it couldn't, but because it relies on far fewer assumptions about the existence of all these complicated epicycles. The Galilean worldview that put the sun at the centre explained in a simple way why it is that celestial bodies appear to rise in the east and set in the west, and why it is that the planets follow more complicated paths across the sky. Further, it made predictions about where any particular celestial object would be at any time on any night of the year with a high degree of accuracy. All of this with far fewer assumptions, unlike the raft of assumptions that Ptolemy needed, epicycle after assumed epicycle after assumed epicycle. Galileo was able to solve this problem with an elegant solution. His heliocentric theory predicted a number of things, including the paths planets followed, and the fact that because not everything had to go around the Sun, the moons of Jupiter could be accounted for. Galileo himself was the first one to discover moons going around Jupiter. The first 4 are named after him. They're called the Galilean moons. Galileo's heliocentric theory could also account for the phases of Venus, and he could explain precisely when they were going to occur. Eventually, all of these things were observed and explained and predicted. So there we have it. Problem, proposed solution, prediction, observation. Now the thing is, Galileo's predictions about the motions of planets was falsifiable. That means it was possible for Galileo to have been wrong. And this is one of the big keys about scientific theories. Falsificationism. The ability for a theory to be wrong. Karl Popper is perhaps the most famous philosopher of science to have ever lived. He was born in Austria in 1902 and is well known not only as someone who developed a theory of how science works and how scientific theories are justified, but also as a political philosopher who produced some of the most advanced and creative theories about how an open and flourishing society should be structured. His ideas are some of the strongest and most articulate against authoritarianism and totalitarianism of all sorts. Now Popper, despite being from Austria, was not a member of the Vienna Circle, although he was in contact with them. He was a critic of their logical positivist philosophical movement, and he rejected the idea that scientific theories could ever be verified. He also rejected their idea that there was no such thing as a philosophical problem. This was a theory put forward by Wittgenstein. He found that what scientists actually do is propose a bold conjecture that seeks to explain phenomena. Scientists then attempt to refute the conjecture. If the conjecture, or theory, is not refuted, then it is conditionally accepted. Now, Popper was a genius, and he did most of his work at the prestigious London School of Economics before going to New Zealand to take up a position at the Canterbury University College in Christchurch. He was rejected for a job in Australia due to anti-Semitism in the late 1930s. Well done, fellas, kicking goals on that one. The view of science that Popper has is really a view of how knowledge in general is created. For this reason, his view is more broadly called Papirrin Epistemology. He saw the acquisition of knowledge as a problem-solving process. At schools around the world now, this underpins the way students learn. At least it's directing the way students are educated more than in the past. There is less emphasis on rote learning and more emphasis on discovery. Students tend to construct their own theories with guidance. The students then test these theories about the world. In science, we call those tests, or attempts to refute the theory, experiments. Those which are refuted are dismissed or altered, while those which are not are conditionally accepted. All knowledge, therefore, is conditional. All knowledge consists of theories about the world. These theories are explanations, and explanations can be good or bad. Your knowledge of science is made up of scientific theories. Your knowledge of history, historical theories. Politics, political theories. Your beliefs about ethics constitute an ethical theory about the world. Your knowledge of what your best friend is doing right now consists of a theory about her. Your theory may be close to the truth, or far from it. It may be based upon much convincing evidence, or it may not be. In other words, your theory may be good or bad. The criteria for good is that a theory explains what it sets out to and explains a broad range of phenomena. The broader a range of phenomena that a theory explains, then the deeper that theory must be. And importantly, a good explanation also makes precise predictions. Consider the scientific explanation that is called quantum theory. Quantum theory is the theory about matter and energy at the subatomic scale. In fact, it explains the behaviour of all subatomic particles. It explains superconductivity and how computer chips work. It explains how fluorescent tubes produce light, and it is quantum theory that enables us to have knowledge of extremely distant galaxies in our universe. The disparate phenomena that quantum theory links is so broad that no other theory comes close. And as for predictions, well, the degree of precision that quantum theory can obtain is like specifying the width of Australia to an accuracy of the width of one human hair. Such bold predictions are just asking for the theory to be falsified, and yet it has not been. As we will see, some of the conclusions of quantum theory are very counterintuitive, but we are compelled to accept them because of the fact that quantum theory puts itself out there to be falsified with highly accurate predictions, and yet it has not been falsified. Sure, one day it might be, but this is not to suggest that we cannot trust quantum theory now. For example, we explain genetic inheritance now through the theory of DNA. We explain that genes are passed from one generation to another via the DNA. The DNA contains a code for producing all of your features under the right conditions. This whole field of genetics, like quantum theory, constitutes a theory. Now, both may be wrong, but what are the chances that DNA has absolutely nothing to do with genetics? What are the chances that everything we know about quantum theory is false? Well, the chances are effectively zero. We may change these theories, but because the predictions they make are so precise, a wholesale rejection of our best theories today is going to be very difficult. But we will have more to say about this in a different podcast. We will also find that it is falsificationism that enables us to distinguish between what counts as science and what does not. Popper's idea of falsifiable theories enable us to explain how Galileo can say things like, on the night of October 27, 1640, Jupiter should be right overhead with Mars at 45 degrees declination, while Venus should be rising just in the east, years before any of these events happened. If he turned out to be wrong, then he would know that his theory was flawed. So that's the method. It has nothing whatever to do with the so-called induction scheme. At no point in the story did Galileo sit night after night watching planets and generalizing a theory from those observations alone. No, there was a problem. The Ptolemaic theory was unwieldy and imprecise. A simpler theory, with fewer assumptions, could solve the problems with the Ptolemaic theory. And this simpler theory is closer to the truth. Now, it's worth noting that the Ptolemaic theory, although way off, could have been worse. At least it had the planets moving in orbits. Sure, they were the wrong type of orbits, but orbits still. The fact that planets move in orbits was something that was true, that was subsumed by the first heliocentric theory, which got us closer to the truth. Copernicus' heliocentric theory suggested the orbits were perfect circles. Now, this was better, but it took a Galileo to improve it further still. Later, the astronomer Kepler, and also especially Newton, improved things still further with elegant laws of motion, which linked the orbits of the planets with the tides on the Earth and apples falling to the ground. Newton's theory rested on very few assumptions, made accurate predictions, and unified diverse phenomena, solving many problems in the process. This is the mark of a good scientific theory. We can never be sure that we have certain truth in science, but this is not a problem for a scientist who is not after certain truth. Scientific theories are explanations, and the best explanations survive. So what about Professor Russell's chicken? Well, the chicken had actually formed a theory in his head to explain the behaviour of the professor before or the moment when he started making predictions. He theorised that the professor was keeping him as a treasured and much loved pet. A prediction which comes logically from such a theory is that the professor will therefore continue to feed the chicken. But the theory was wrong, and it was falsified in a dramatic fashion on Christmas Day. As I explained earlier, if the chicken had developed a theory which correctly explained the farmer's behaviour, namely, why is it that he is being fed each day by the farmer, then the chicken would have formulated the following theory. The farmer is feeding me because he wants to fatten me up for Christmas dinner when he will eat me. The point is that any number of theories can explain a set of observations. In order to make a prediction that a certain phenomena will continue to occur, you first need a theory in mind that explains what's going on. That theory would explain that the phenomena is going to continue, or perhaps it will explain that the phenomena is going to stop. You see the sun rise each day. you don't simply conclude on that basis alone that therefore the sun will continue to rise every other day. In fact, that's not a scientific theory. That's just a prediction. And science is not primarily about predictions. It's about explanations. The explanations will allow you to derive predictions. That the sun has risen every day might, conceivably, give rise to a problem. A problem like, why does it seem to be the case that the sun rises in the east and sets in the west each day? Or, what is the sun at all? To solve this problem, you need to use a theory. Now, at the moment, the best available to us is the theory from astronomy and astrophysics and physics and a whole raft of sciences that go on to explain what the sun is and how it works and why it is that it appears to rise in the east and set in the west. In this case, the full armamentarium of science would explain to us that the sun appears to rise due to the motion of the earth, and this motion is not expected to cease for billions of years. Well before this, but still billions of years from now, the sun will cease shining. However, this will not occur in our lifetime, and all of this allows us to predict that the sun is going to continue to rise each and every day of our lives. So if you read some texts on the subject of how science works, including various resources about TOC, you will find an erroneous scheme. The claim is that scientific theories are produced in the following way. You make observations, you generalize these observations into a theory, you then make more observations, and these justify the theory. And it is this scheme I have argued, along with Popper, is clearly false. The way science actually works is in the following way, and I have taken almost everything that I've said here directly from a scientist I have mentioned before, David Deutsch. Science works by first identifying a problem. It then suggests solutions which possibly solve the problem. These solutions are criticized. Now in science we include among our methods of criticism a special type called experimental tests. These experimental tests then enable us, possibly, to replace our erroneous theories with the ones that solve the original problem. We may then encounter new problems to solve and the cycle begins again. At this point, I want to highlight a link that exists here between science and mathematics. We have seen that induction in science, indeed induction as a means of justification in general, simply is not a way that we reason, not a way we can reason or do reason. The logical positivists, textbooks, and common sense are all wrong. But in mathematics, there is a procedure called mathematical induction. What about it? Mathematical induction is a process senior students of mathematics learn in order to prove certain theorems. It is a very valuable and useful means of proof, and it is deductive. Let me say that again. Mathematical induction is a deductive process. Unfortunately, it shares the term induction with that other induction we just discredited, but the two are entirely different. Some TOC texts, and even some maths texts, allude to the idea that mathematics uses induction, that naive induction, to establish certain mathematical formulae as true. This is incorrect. For example, consider the following surprising fact about odd numbers. The number 1 is equal to 1 squared. Okay, big deal. Stay with me on this. 1 plus 3 has 2 terms, and it's also equal to 2 squared. Alright, 1 plus 3 plus 5 has 3 terms, and it's equal to 3 squared. Okay, let's keep going. 1 plus 3 plus 5 plus 7. Notice what I'm doing here. I'm just adding up all the odd numbers. 1 plus 3 plus 5 plus 7. That's got 4 terms, and you guessed it, it's equal to 4 squared. So the pattern seems to be that for however many odd numbers you add up, then the sum of those numbers is equal to the square of the number of terms that you've added together. Now, naive induction would say, well, you can conclude on the basis of what seems to be going on that that's actually the case. So an inductive proof would be that any sequence of odd numbers definitely adds up to a square of the number of odd numbers that you've added up. Proof done. No, no, no. I presume you'd get your backside kicked pretty hard in mathematics class if you tried to prove anything this way.
No one in mathematics ever tries to prove a theorem in that way, certainly not at university and not at school. That sort of induction just doesn't have a place in mathematics. So why would some texts that explain the way that mathematics works even mention that this is a valid method of justification? I'm not too sure. I know that what such an argument would do is that it leaves the door open for anyone not fully trained in mathematics to be able to say, you can never be sure that your proof will not fail for a certain number of odd numbers. So, for our example, how do you know that the formula doesn't fail once you get to, let's say, 1,354,291? You can't be sure. So, mathematics is unreliable. Well, if indeed we were proving our theorems in the way that I've just described, then yes, that'd be a valid criticism. But no one in mathematics proves things the way we just did there. But you can use a technique called mathematical induction to prove it. Now I know, these uses of the word induction are confusing. Induction does have a lot of different meanings. If you look it up in the dictionary, there are quite a few there that haven't even been covered by what I've been talking about so far. But suffice it to say, in real mathematical induction, the method of proof known as mathematical induction, what you do is you check that the formula works in a particular case. So usually for the case of the number 1. In our example of figuring out what the sum of a certain sequence of odd numbers adds up to, we can take the number 1. Okay, 1's an odd number and 1 happens to equal 1 squared. Plain and simple. Well, then you assume that the formula works for a certain general case. So we could assume that it works for 1 plus 3 plus 5 plus all the way up to k, where k is some odd number. And you assume that that equals to n squared, where n is the number of odd numbers that you've just added up. Then you take this assumption and you show that if it holds, then it's the case that it works for the next number, up to all the numbers k plus 2. This would be the next odd number. For those taking higher levels of mathematics, the proof of what I'm talking about right now accompanies the notes to this talkcast. Now, I'm not going to attempt to go any further with the proof. It's almost impossible to teach mathematics purely via audio. Suffice it to say that mathematical induction can best be compared to dominoes. You push one over and the rest is certain to go over as well. It's a rigorous deductive mathematical proof. As certain as anything else in mathematics, it's not naive induction. It has none of the flaws of naive induction. Its only flaw is that it's called mathematical induction. It should be called proof by iteration or something. It seems to me that this unfortunate turn of phrase gives much fuel to some who want to suggest flaws with mathematics. Now, if you've heard the other talkcasts on the nature of mathematics, you know that there are sensible and very interesting discussions to be had about the reliability of mathematical knowledge and its limits. But mathematical induction, and induction in general, are not included as part of these limitations. The limitations and reliability of mathematics are actually far more interesting than this stuff about naive induction. Now, finally for this episode, I want to emphasize that my criticism here of the entire idea of induction is not shared by all. I said in the very first episode of Talkcast that I would be presenting, at times, a decidingly one-sided view of reality. We don't have time to go into all the details about the debate here. Indeed, some people still believe in induction, and they believe in a certain type of induction called Bayesianism. It's quite popular among some philosophers. But I think that that's induction in a cheap tuxedo. As always, these alternative views are definitely worth researching, and we can continue the discussion online. Now, having spent an entire episode talking about what science is not, next time I'm going to talk about what science really is.
For resources and links associated with Talkcast, visit the Talkcast website at www.talkcast.net.